this electron which is reached here, that there is another electron presence, and so this electron able to know the presence of this electron by exchanging photon as a virtual particle, and this interaction, as you know, is known as quantum electrodynamics, because two electron, which is light particle, they are charged particle, and when two charged particles or charged electrons they are coming together, they basically recoil each other or repulse each other. And that recoil basically happens because of the exchanging of photons. So what Feynman did, he basically tried to draw a diagram here like this, and that basically helps to visualize how the interaction happens. And then why I'm talking this one, because when I consider this QED, one of the very fundamental symmetry, this mathematically, we'll try to understand what does it mean. It's called E1 symmetry. So why this one here? This one is basically unitary transformation, or it's called unitary. So if you consider a unitary matrix, this basically one-dimensional unitary matrix. So if you remember in mathematics, when you consider something unitary, we call it something. Yeah, please.
Yeah, I got you. Yeah.
Yeah. So
So
it will.
like there's transformation, right? I mean, the rotational is one type of transformation, translational is one type of transformation, and then reflection is another type of translation. So when you say U1, are we referring to all the three, or referring to only one? Any one?
So actually, this U1 is it's not literary meaning of U1 rotation. So this is one of the representation of that. So, but usually when you're talking about the, let me first define symmetry. What I mean by symmetry. Let's consider if I consider this cup. So that's how I able to understand what the symmetry means. So if I just look into this cup, like it has a symmetric nature. If I just for a moment I just forget this one, yeah, handle, then it has a symmetric nature, right? I mean, if I just cut in like two pieces, I can get to symmetric picture. So symmetry is like after the rotation, uh, and before the rotation, if you consider rotation of one of the axis, like if I consider a triangle, and if I rotate this triangle about this axis, let's first take a one rotation like 120 degree, and then one more rotation 120 degree. The form of this triangle, it will remain same. Yeah. Or if you just look in this part or this part, they are identical. So there is a symmetry between both the sides. So symmetry is one of the very important picture in at least in the quantum field theory. Like if you remember in the very beginning first class, we were talking about how the particles are generated, and one of like when we talk about the Higgs, so the discovery of Higgs happened, or Higgs was generated because of the symmetry broken. It was spontaneous symmetry broken. If you remember, we discussed about this Mexican hat one. We'll go in detail later. So when you consider Mexican hat, and if I try to draw the Mexican hat, yeah. So if you consider like a kind of like uh, bottle, which are if you just cut off this top one, and if you take a ball and put it, so there is one stable position, there is one stable position, there is one stable position. So if you put a one ball here and give a little bit of force, if you just give some perturbation, additional perturbation, so this ball will be either move in this direction if the force is from this side. If it's this side, it will become here, and then this ball will be start to oscillate about this point, because these two also equilibrium point. So it will start to oscillate like this and oscillate like this, and at some point it will become at rest. Okay. So this is kind of like a example of a symmetric potential. So if you consider this one, if I consider a ball, when it will be at this point, it can easily stay at rest if there is no additional perturbation. But when I start to move from here and I reach at this point, this is a kind of stable point, but if you just give a little bit perturbation, the ball will be moved in one direction and another direction. So with respect to this one, there is a symmetry, but at this point there is asymmetry because the physics at this point and this point are not same. It is a stable equilibrium point. If until unless there is no additional perturbation, this can stay here forever, and also same in here. But at this point, this ball it is not a stable position. It can oscillate about 1 point. So we'll discuss in this later when we talk about the Higgs one. And whenever there is some symmetry broken at some point, like in case of this, when there is continuous symmetry broken, we'll try to understand what the continuous symmetry broken means. Then a new particle is made. So symmetry is a very important concept. What we always try to understand in physics, because if you consider the Newton law of motion, that famous one, F equals to g times m1 m2 by r square for two massive objects. So Newton law is a symmetrical. If you consider in any position in any coordinate system, it doesn't matter in which coordinate system you consider, but the Newton's law of motion will be identical. So symmetry was a very important concept in physics. But whenever there is a possibility to broken the symmetry, some new physics come up. So it is important to understand the concept of symmetry in our picture before to go into more.
Got a bit actually. Like this, what I understood. For example, like I mean, the Newton's first law of motion, a object stays in uniform velocity unless or until it is disturbed with external force. Right. For that law to be to work, there should be a symmetry. There's like translational symmetry should be there.
Yep.
The ball behaves in the same way, whether it's this part of the space or whether it's in outside the galaxy. It behaves in the same way. Let's assume like there's no planet, but the behavior of the ball will be same in this inside the solar system, or if you go outside the galaxy, it will be the same. So that is why it is symmetry, and then the time symmetry. Like whatever we say right now, it will work like even billions of years later also. So
Yes.
that's what I understood about the symmetry.
Yeah, the thing is that yeah, you're right. So also, as I mentioned in the very beginning of our classes, that also there is one important thing why symmetry is supposed to be there in the nature. Like and that's because of the conservation law. Like when I consider you're talking about when I consider in terms of space. So if so, and I just so there is a two rigid point here and here. And if I so this is everything is fine, and I give some perturbation here, additional perturbation. That is kind of like string when if you play some musical instrument, then it start to create some wave vibration. So what will happen? The wave it start from here, then it reach at this point, and then it will be again come back. So at this point, and so if I consider the wave which is moved, if I consider once again just try to draw the wave in terms of wave. So one wave reach at this point, and then the wave, if the wave is moving return back like this way, then the so in one cases your momentum was around this direction, and in other cases your momentum was around this direction. So it is positive momentum if I consider a positive reference, this negative. So at this point, when the wave is go and reach at this point and return back, let's think in this way. It not really happen, but if I think in this way, then when it's moving in this direction, your momentum was positive, but when you return back in this direction, its momentum is negative. So here in this case, at this point, your momentum is not conserved because in one case it is positive, but at this point it is negative minus t. So momentum is not conserved. So, like if I try to solve this kind of problem, there is one very important trick what the people are used. So when they try to solve this kind of problem, so there is a boundary, right? So whenever there is some boundary value problem, what one can do, instead of considering that it is end at this point, I can do one thing. I can make it a circle. So whatever the initial point, it starts from here. So that's if I consider a basically a rod or a basically string, it was a long thing. I can just pull it and make it like a circle. So whenever the wave is starting from here and whenever it's reached at this point, the direction of momentum will still remain same because it is moving like this way, right? It is moving like this, then it's again moving like this. So at this point, so see there, if we consider this one, so there is a certain possibility of momentum conservation is broken, and there is no momentum conservation at this point. But here one can solve this momentum conservation problem instead of considering a string, which is at the boundary here, we can make it a circle one. So one can very easily tackle this problem when there is a boundary where the momentum is not conserved. Whenever there is momentum is not conserved, there is a corresponding symmetry, which is a positional symmetry. Like if we move from x to minus x, like if you consider a function which is a x to the power 3. So I consider a function which is a sq function, and when we change from x to minus x, it is minus of x cube, which is equals to minus of f of x. So if I consider something like this, if I change the position from x to minus x, then so this kind of if I try to draw this function, it will be something cubic function, which is not. If I consider x square, it will be something like this one. I guess x cube will be something like this, something yeah, which is not a symmetric one. So whenever there's some positional symmetry, if you go from x to minus x or minus x to plus x, so if you like if I consider a function like x square function instead of x cube, which is a symmetric function, okay, and in this case, if the particle is moving from this direction or particle is moving from this direction, your momentum will always conserve. Okay. So, but if in some places, like if I consider a function like this, why this what happened? If I consider a function like this, which is not a symmetric one, suppose if I put a ball here, the ball is moving here and it will be moving like this way again. But here in this case, ball is coming and it will again come back. The momentum will be constant if the particle is oscillate about this one. Yeah, there is actually this is theorem. This is theorem is called as Noether's theorem. Yeah, so this is a lady who gave this theorem, theorem, and the theorem states that if there is a symmetry, that means there is an underlying conservation. Like when there is positional symmetry, momentum should be conserved. When there is time symmetry, the energy should be conserved. And you can think this way also in terms of your Heisenberg uncertainty principle. Like there is a, though it is not really one-to-one correspondence, but if I write delta x over delta p of the order of h square. So the position and momentum they are interconnected. Also there is something like delta E dot delta T very equal. So when there is a positional symmetry, then your momentum should be conserved. When there is time symmetry, then your energy should be conserved. And this is yeah
Actually.
yeah
Like in the Griffith, I know it's a small deviation, But in the Griffith book, right? I mean, the problem that we did during the last class, where one proton is at rest, another proton is like coming and colliding with that rest proton, and then it creates four protons, three protons, and one antiproton. So in that scenario, the Griffith was saying that the P total on the left side is not equal to P total on the right side.
Yes,
But P square total on the left side is equal to P square total on the right side. But P total is not equal.
it is. I mean, no. Okay, like if I just write that once again. Yeah.
The position symmetry has to be there, so momentum will be conserved. So in this case, like, did the position symmetry break? But does it mean like that same experiment, if it done in a different location, uh, the antiproton will not come? Like I am trying to connect the.
Okay, so in this case, it's not one-to-one corresponding when I consider about this proton and the proton. But yet in this case, this antiproton was created just to make analogy. Because suppose if I consider two protons, which is was at rest, one proton was moving, so this proton has some momentum. It was at rest. And after the collision, you have four particles, two protons. They are also moving, but you have still some enough energy to create, because also we calculate the amount of energy what is needed for these protons. So this proton has enough energy to create another particle, this antiproton, and but this what I was trying to explain that this antiproton, if I consider this only antiproton, then the momentum will be not conserved. Because it is this other particle along with it which can conserve the momentum of for this antiproton. But in that case, yeah, this positional symmetry is what the story is here. The story is these two are not really one-to-one corresponding, because to understand the creation of this antiproton, we need to go into the region of where the quantum electrodynamics or quantum chromodynamics come into picture. So yeah.
What condition will we have like a like a break of conservation of momentum? In what condition do we have break of conservation of momentum?
Yeah, like exactly take one example like this one, the classical example I was talking about here. So, so if I consider one particle, let's just think in terms of particle. The particle is moving along this direction. It's a positional, right? It is moving along x-axis. So in this case, when it reach at this point, let's consider this is the x-axis. When it reach at this point, it's moving along the x direction. It has a positive momentum. But when it's moving in, okay, just to complete this one. So when it's moving in the backward direction, which is like minus x. So in this case, you can see your momentum was plus p here, and here it is minus p. Yeah, yeah.
Yeah. So in the case of antiproton, if we draw the four vector for antiproton, how does it will look like? For a proton, it look like mc omega comma mv omega. For antiproton, it will be like a minus mc omega and minus mv omega.
If I want to write the four vector in case of like this one here, so if I consider so just we need to, so this is my protons which was moving, and the other proton was at rest, and after the collision both the protons are moving and there is also momentum. So suppose this is the proton one and this is the antiproton. So whenever I write the four vector, so these two are the residuals. This is your projectile and this is your target. So the projectile, let consider target is move along this direction, projectile is move along this direction, and this is your proton and this is antiproton. So when I write the four vector for this proton and for this antiproton, the momentum vector component that should be negative of each other. Yeah, that's what was my point. Like This momentum should, this antiproton should be moving in the opposite direction of the proton so that they can conserve the momentum of each other. And these two this projectile and target, they conserve the momentum from the incident proton and the fixed target, because the target was at rest, like it does not have momentum. So they share the momentum between them, and this proton and this antiproton, they share the momentum to cancel out each other. So that initial momentum and final momentum, four vector, that should be conserved. Yeah. But the important thing, what we need to keep in mind when I talking about the symmetry one, what the Neutron's, so actually we able to derive, we able to show the Neutron's theorem when you start to, if I do some mathematical calculation considering quantum electrodynamics or QED or even quantum field theory, it is possible to derive this conservation law, and it is possible to show that. I mean, I can at least show for one of the conservation one in the next class. So what I will do, I consider a potential which is called phi 4 potential. I'll consider phi 4 potential. So this is a kind of potential we then what I'll do, I use there is something called Feynman path integral. So I'll use the Feynman path integral approach, and then I'll do some mathematical calculation. Though it will be boring, but it will at least good to show at least for one that whenever I say that if position is conserved, I mean if the positional symmetry, then momentum should be conserved. So this will be, for now, I'm just giving a statement, but in the next class, I'll do the mathematical calculation, and then I try to show that it is not just a theorem, not a statement, but in quantum field theory, it is possible to show that your if there is a positional symmetry, that means your momentum should be conserved. If there is a time symmetry, then energy should be conserved. So this will be, I'll do in the next class, because it will take some time to do the derivation. So, and also in next class we'll try to learn something called Feynman path integral formalism. There are many formalism in quantum field theory. The easiest one is Feynman path integral, because Feynman is, he always try to make things simple. So we will consider the Feynman path integral approach, and we'll try to understand how one can show the statement that if there is a symmetry, that means there should be concept quantity. Okay, so this is about the quantum electrodynamics. So also in the next class, I will try to, when I do the derivation on the way, I will show you what do I mean by E1 symmetry. So, and we will try to understand in at least for one, at least not for other chip, at least for QED, we will try to understand how the E1 symmetry come into picture and why E1 symmetry is important for the QED or quantum electrodynamics. If we are able to understand at least one for QED, then we can just try to use an intuition to understand how mathematically one can think there will be symmetry underlying for QCD and weak interaction also. Okay, so just to, yeah, yeah.
So you mentioned like when there is a time symmetry, we'll have conservation of momentum. And
No, when
sorry,
there is position
yeah,
of energy,
position is momentum, and there are time is energy. What symmetry has to happen for a conservation of charge?
that's actually it's not something very easy to say, because charge conservation is a very fundamental conservation one. And whenever we consider the charge is not conserved, uh, we will see when you do this QED derivation, then I will mathematically show exactly what will be the conserved quantity for charge growth if the charge is not really conserved at some point.
So in a
Okay.
simpler layman terms, time symmetry means when I'm doing this experiment now or a billion years later, we'll have the same result. That is time
Yes,
symmetry.
this is time reversal. Like it's like usually we mathematically say that when t goes to minus t, then the underlying physics will be remain same as it was in time. So it will not time dependent. It will be independent of time. Okay, so now next thing what I just to complete the introduction part. So this is about the QED. When two electrons they came to closer to each other, they exchange the virtual photon, and by exchanging virtual photon, they came to know the presence of other electron, and they interact each other. And the dynamics is quantum electrodynamics. And so here this photon is basically so these two are fermion, which is having the spin half statistics. Like remember in the last class, I was when we do some dimensional analysis for I think it was for Planck constant, and I saw by dimension analysis that the dimension of Planck constant is also equals to dimension of r times dimension of p, which is the angular momentum. So for these fermions, which is have half a cut spin or spin angular momentum, and for boson, and it is also for the Fermi Dirac statistics because that's called fermion, and all the boson they had they for the Bose-Einstein statistics, and they had integral of h cut. That's the corresponding spins they should have.
Say
Interaction.
quantum, sorry, in one
Sorry.
line, the quantum electrodynamics is study of uh, dynamics of charged particle, especially electrons.
Oh, sorry, I cannot catch your question. Can
Like
you?
in one line, if someone asks me like what is quantum electrodynamics, it is a study of charged particle like electrons.
So yeah, it's basically when we consider the dynamics of light charge particle, and when the fermions are the interacting particle like electron, muon, tau, those are the fermion, and the exchanging particle or exchanging bosons are photon, and this dynamics is known as electrodynamics. This come the what comes to like electromagnetic when there's some electromagnetic interaction, and then the interaction is happened because of the exchanging of photon. And this physics is the underlying physics is known as the quantum electrodynamics. And why it is quantum? Because the physics, if I try to understand, it is not in the classical picture. To understand the dynamics of these two electrons, they are interacting each other by virtue of virtual photons, which is like a gauge bosonic particle. To understand this dynamics, classical picture is not enough. So we need to go to the quantum picture where all this quantity like H cut is an important quantity. So we are thinking about this scale, this energy scale. So it is not classical one, it's quantum one, and the dynamics is basically studied for charge particle like electron, muon, and they exchanging virtual photon. Yeah, it could be like electron, positron. So, like as you know, all particle has antiparticles. So electron has a positron, muon, mu minus and mu plus, and tau also at tau minus. Okay, so the next thing in our list is weak interaction, and the weak interaction is the most interesting interaction in nature because this is the one thing which help us to go into even more deeper. Because when I talking about quantum electrodynamics, we are considering the fermions level. We are considering electron, muon, tau. But when we consider the weak interaction, then we are going into deeper mode in the quark level. So if I just try to explain at least one electroweak nuclear interaction, as I mentioned in the very beginning class, that electroweak interaction come into picture when we consider decay. So, like if I consider one Newton is convert to proton, there will be one electron and electron anti-neutrino. When they are high energetic, then the neutron from neutron to proton, and then it generate electron and electron neutron. So if you remember the quark structure, probably once we will come into more details because the neutron it is formed by uh, one up quark and two down quark, and this proton it is formed by uh, two up. Let's light right. I light like this way. So two up quark, one down quark, as we said. So let's try to understand how this interaction happened using Feynman diagram. So first, what actually happened here? This up quark and this up quark, this down and this down quark are remain as it is, but this down quark is converted into up quark. And how this happened? So if I consider, if I just try to draw, so this up quark is given up quark, this down quark is given down quark, but this down quark, when it's converted to a up quark, so this is up, down, down quark. It is remain up quark, remain down quark, but it's changed to up quark. So this down quark, when it's converted to up quark, then it exchanges a particle which is known as W minus particle because at this point the charge should be conserved. So this is proton. So this is neutron, which is a neutral particle. So it's converted to positive particle. So it's supposed to emit one negative particle in any form, so that the charge should be conserved at this point. So it emit one W minus, and this W minus is further decay into one electron and electron antineutrino. And this antineutrino comes because the lepton number also should be conserved. You had one lepton here, but so this number supposed to be conserved by this antiparticle. So it generates one antineutrino.
Okay, I understand. I understand that. So why don't we not have why we are having anti-neutrino, anti-electron neutrino? Why can't we not have
Yeah.
a
So
electron neutrino?
whatever the neutrino it will be, it's supposed to be electron like E-like because you had one electron here. So you need one E-like particle. So this one. Now this electron, if I think it has a lepton number one. Yeah. So you need whatever the particle it will be, the corresponding lepton number should be minus one. So energetically favorable is a neutrino one, which is like a very tiny particle because when this W minus is further decaying, and this W minus having mass is of the order of 18, I think, giga electron volt. Yeah, this W minus has mass like 18 giga electron volt, and this electron has energy of the particle. But this whatever the particle it is energetically, it should be very high energy particle, and also it's the mass. We'll try when we discuss about neutrino in a special class, then we'll try to understand why this neutrino, according to standard model of particle physics, this neutrino is massless. If you look into standard model of particle physics, this neutrino is considered massless and left-handed and right-handed. So we'll discuss that later. But in the standard model of particle physics, the neutrino were considered as a massless particle. But later, when there are different experiments happened, one in Japan, there is experiment at I think in US, UK, and this Japanese colleague when they did this experimental study in superconductor, and they measured that they find that neutrino they oscillate their favor. We'll discuss in later in one special class when talk about the neutrino oscillation. And they studied and found that the neutrino is oscillate. And when they calculate, oscillate means so one flavor of neutrino, like electron neutrino. So there is three flavor of neutrino, muon and tauon. So let's consider at the sun when the neutrino are created. So they basically created muon neutrino, and when they let's consider this is muon neutrino, and when they measure in the earth in different experiment, and they find out the neutrino which is created at sun as a mu like neutrino, the amount of neutrino what they calculated which are created at Sun, and the amount of neutrino they measure in different experiment in Earth, they find that the expected neutrino flux is number of neutrino per unit area unit time, expected neutrino flux and the measured neutrino flux, there is a deficit. That is not exactly same. So whatever the muon neutrino is generated here and the muon neutrino they measured here, that is not identical. So there was a possibility they find that okay, probably this neutrino which has the other two flavor like electron neutrino and tau neutrino, this neutrino can change their flavor. They can change from electron neutrino to muon neutrino or muon to tau neutrino or in other way around. And then they try to find they define the probability. What is the probability of a muon neutrino convert into electron neutrino when they reach suppose they move they they travel the distance L and the energy of neutrino that considered nu, and they try to calculate what is the probability of this muon neutrino to reach the distance L, and they find out that probability, which is whatever it will be, is depend on let function of the mass. So there's a big formula. There is like sine square of theta and sine square of delta m square. So delta m square is the mass difference between two flavor of neutrino. And there are some factor, additional factor here and with something here and something here. We'll see later. But what is the picture here? The picture is that whatever the neutrino which was created at sun when let's consider it is muon neutrino, and when they reach to earth, the possibility it can convert or change its flavor from muon to electron or electron to something else or muon or tau. So there is a possibility that they can change their flavor, and what is the probability of doing this change is depend on the
Mass difference between, yeah.
mass difference between two flavor.
So so the sun releases muon neutrino. So if the delta m between muon neutrino and then electron neutrino is higher, then the probability is higher to change to electron neutrino.
And when they calculate this probability was non-zero. It was not, and when it is non-zero, that means this change happened when the electron neutrino is created and it reached to the earth or muon neutrino created reached to the earth. The probability of make this change of the flavor from one flavor to another flavor is non-zero, which corresponding that this mass difference, or that means this neutrino should have some mass because of that this oscillation happened. It's called neutrino oscillation, and it was a long time problem. There is it's called solar neutrino problem or solar neutrino. Yeah, it's called solar neutrino problem. It was a long time problem, and then when they discovered that this possibility of making this oscillation from one flavor to another flavor is non-zero, which corresponding that neutrino has some mass, and that actually violates the basic concept of standard model particle physics. Of particle physics, when they do the mathematical calculation, consider the right-handedness, left-handedness of neutrino or anti-neutrino, and then they find that there is something beyond standard model. So one new physics started. It's called beyond standard model physics, and neutrino is one of the important candidates in standard
Yes.
model.
Yeah, I read that it didn't have the chirality, the right-handed.
Yeah, so yeah, there's a different
Yes.
chirality. It's called also different handedness. It's called left-handedness, right-handedness. So yeah, so this neutrino is an important one because of this massive nature of neutrino, it basically gives a signal that we can think something beyond standard model. So standard model is not everything in particle physics. There are now many physics going on which is beyond standard model of particle physics. Yeah, yeah.
So the W minus in this diagram is says 80 giga electron volt, right? I'm always confused between when you say mass, right? I mean like the for the fundamental particle we know a mass, that mass is constant. But when you say like this particular W minus has 80 giga electron volt, does it mean it has more energy, or does it mean like there is many W minus? What does it mean?
like in the last class we discussed about, like if I consider this relation E equals to mc square, so if I consider c equals to 1, so now we are in the picture in particular physics where we consider between c equals to 1 or h equals to 1. So here your e is equals to m. So whatever be the mass of this particle, that is, we can convert this into, we can write in terms of energy.
This is like okay. Let's start with the basic one.
Yep.
When a in a standard model, W minus has a particular mass, right? If you take a
Yes.
standard model, um, just for an example, we say like W minus has a mass of 10 GeV. Just for
Hmm.
an example.
Yep.
Now here what it has released is 80 GeV. Okay, so the difference is like 70 GeV. That the difference 70 GeV appears in the form of energy or appears in the form of like another 7 more W minus comes.
From energy. That's why we call it high energy particle. Because this particle which having mass is obviously, when you consider the mass of W minus, no one is going to take a like a weighting machine and take the W minus into the weighting machine, measure the W mass. So how they do? They basically measure the energy, how much energetic it is. And when they know the energy, and from then this God-given equation E equals to mc square or p square c square plus mc over 4. If I know the momentum of the particle, then I can convert what is the reaction mass of the particle. So usually when I consider 18 GeV, it is mean it is a energy, how energetic it is. Because in high energy physics, we treat mass and energy in the kind of same footing. We consider they are identical, not identical, but they are equivalent.
See, when we say 80 GeV mass, what we are actually saying is like 80 GeV energy, like it's a very high
Energetic
energy.
particle. Yes.
Okay,
Yes.
okay.
So as you're talking about the mass one, it is also important to note that when I consider this change from neutron to proton, which is Newton, usually if I write down the mass of Newton, which is so till now we are in the picture where we consider uh, Newton is converted to proton, and if I look at, yeah, it is spontaneous decay to a W minus. It is not really spontaneous. That's what I am trying to make a picture. It's not really spontaneous. It took some time, and we try to understand how much time it need. This when the proton, this actually in if we consider high energetic uh, neutron, it also needs some time. It's of the order of 15 minutes to make it a change from neutron to proton. It's not spontaneous one. And one of the reason behind that, if I consider mass of proton, which is, so mass of neutron is like one MeV difference. But this one MeV energy is very important because this W minus, which is a massive particle, now that is massive particle is more energy. Now there is a relation of Heisenberg uncertainty principle of H cut. So this, what this relation tell you, that suppose you are taking some energy from something, and whatever this, so my question is, so like if I consider the mass difference between neutron and proton is of the order of 1 MeV, and the particle is created is of the order of 18 GeV. So the question is how this 1 MeV mass difference can create this 18 GeV energetic particle. So the answer is it's actually coming from here in a very naive way. It's not really the very deep one, but if I try to understand very naively, that whatever the energy you take in, what are the energy difference between this and these two, if I multiply it with time, the amount of time this taken to get that energy, that product will be of the order of 10 to the power minus 34. And if I give that amount of time to take that energy from this to this, and that will be, so this one MeV energy difference, whatever the energy difference it was, this one MeV energy difference was enough to provide with a particular time frame, like 15-minute time frame, one can do the calculation and calculate what amount of time it needs to do this exchange. And that time was enough to make a transition of one down quark convert to up quark, which can create one W minus, and this W minus, which is like 18 GeV energetic particle, can later convert into electron and electron neutron. Is it clear?
So what you're saying is that when a neutron, when it is addressed, it absorbs energy. It takes the time to absorb energy, and then once it has reached some critical point energy, then it decays into proton and W minus.
Yes. Yes. So if you take a pen and paper, if you calculate how much time this energetic particle, when it's up like energy 18 GeV, if you consider speed of light into, because this is very high energy particle, if you consider this W minus is moving in a very high speed, close to speed of light, not to be exactly because it can't exactly move at close to speed of light. It's not each photon, it's W minus. If you consider the high speed, then you can calculate how much time it can take when it have energy 18 GeV, how much time it can travel with the speed of light. And if you calculate this one, it is possible to calculate the time which is of the order of 10 to the power minus 25 second. So I have this number. So this time, this W minus before it decay to electron and muon, electron antineutron, it can take like 20, 10 to the power minus 25 second, which is like which is very small time scale. Within this time scale, it cannot even travel to the proton itself. So within a, because if you remember the length of the time radius of proton, which is of the order of femtometer scale, 10 to the minus 15, and the time is 10 to the power 25, and it at a very high speed. So you can calculate how much time it can take to travel this 10 to the power minus 15 meter or 1 femtometer. Let's go say 10 femtometer. So, so this is a very small time scale. So within this 10 to the minus 25 second time scale, this high energy particle decay further into electron and electron neutron.
I understand what you're saying. So yeah, got you, got you. Then how did we detect that W minus is coming?
How did it derive?
How do we detect that the W minus?
So it's not that's the thing. This time scale is so small. If we want to measure this one, we need to go to the corresponding length scale. Because 10 to the power, if I consider c equals to 1, so you can calculate c is equals to delta r over delta t. So you need a time frame. If you consider c equals to 1, so your delta r and delta t is identical. So you need a frame of reference which is of the order 10 to the minus 25 meter of the order of, because I just take approximation. So, but what we know this particle was there because we know the final set of particles. So this final set of particle, like when the Higgs was discovered, it was not that Higgs was really observed. What they did, they observed the corresponding total particle. They know if the Higgs decay, then what will be the corresponding total particle one can observe. So this electron neutrino, if in any experiment they observe this electron neutrino, electron antineutrino in this case, that's basically a signal that there was a W minus particle, and this W minus was coming from this exchange, because it's not possible to really till now, because our energy scale is not up to this frame of reference of 10 to the power minus 25 second. So if at some point if we able to even go more high energy, if I have an accelerator or some detector where one can study this 10 to the power minus 25 second, then it's possible to see this this W minus is decaying. So it is experimentally verified that, yeah, just one second. So it is experimentally verified that this W minus was there because this electron neutrino is experimentally verified. Yeah.
Right. Yeah. Got you. So two questions arises for me
Yeah.
actually. So question number one is like the delta E delta T is equal to approximately H bar. So does it mean that see delta delta P delta M is equal to H
Delta
bar
P delta X.
then
Delta P delta X. Sorry.
delta
Yeah.
p delta x. Sorry, delta
Yeah.
p delta x. That again. So yeah, that is equal to approximately h. So basically, like this is the smallest momentum that you can define. So what I'm saying is like when I say delta e delta t, right? If I measure, if I start measuring the energy of a particular particle, I can measure. I cannot measure instantaneous. I can measure only like a I can measure only. So, okay. Uh, what I'm trying to say is like when the W minus goes to neutrino, if I measure it late, then the neutrino, if I start, like if I measure it the moment that decay happened versus if I measure it the after some time the decay happened, will the energy be different? So that's what I was about to say.
Yeah, yeah. Not like this way. Even if you think on the Heisenberg uncertainty principle in terms of delta x over delta x over delta p is is basically less than like I can say of the wage cost. So if like yeah, whatever you said, it's true. It's true in one sense. If we try to understand just physical way, like if we measure the position with high accuracy, that's important one because this is actually the delta x, which measure measurement of uncertainty. If we measure the uncertainty to measuring position, if it is very low, very small, then you can measure momentum with more high accuracy or more uncertainty. So what here I am trying to make the story in that way that let's consider whatever this W minus particle. Actually, you can understand. Let's try to make into more deeper one how this W minus is actually generated. Okay, then probably it will be more interesting. But this is very interesting story. I mean, there is not much mathematical derivation to do this one, but it's very interesting story to understand in terms of Feynman diagram. So now we are mostly focusing on how this W minus generate. So let's for a second we consider that this D quark, which is further convert into up quark. Okay, so let me just draw this one. This D quark will remain D quark, and it create one. Okay, so my final state was this D quark, which was changed. This down quark was changed to up quark. And how this change happened? This up quark is created what anti-particle, is anti-up quark, and this down quark. If I think in this, so the down quark is given as down quark. So this up quark and this down quark, they together form this W minus. So actually, when this down quark is converted to up quark, then this W minus is getting energy from the vacuum because this one is created instantaneously within a very small time scale, and we basically call it this particle is created. When it's created, it so this neutron and proton, there is a small mass difference, and because of the presence of that mass difference within a particular time frame, it gets enough amount of energy from the vacuum, and that basically help to create this W minus particle. And this W minus, so this is kind of just imaginary way one can think how the particle, because your down quark is remain down quark. So your down quark is convert to up quark, and this up quark it cannot create automatically, right? Whenever any particle creates just be antiparticle. So this this down up quark and its antiparticle, and this the presence of down quark, so they together form this W minus. So whatever the energy this W minus get is basically the amount of energy is taken from the vacuum when they create this. this virtual particle, and this time frame to get that energy from the vacuum, if I consider that is a delta t, and then the amount of energy this particle should have is of the order of h cross. Or even if better way to use, I think the mathematical one is less than h cross. So this what I find is the amount of energy is taken from the vacuum to generate this W minus particle, and the time amount of time is taken. So that should be less less than this quantity. So it should be very fast, very spontaneous. Or if it does not have enough energy, then it takes more time. The amount of time it will be taken, we should follow this mathematical formula that the amount of energy taken times the time, it will be of the order of Planck constant.
So that does it not does this not opens a can of worms? Like when you say like energy is being taken from vacuum, is that
Mhm.
like where's the energy coming from? Like that means like how the energy of I mean conservation of energy will be broken, right?
No, no, it will not broken here in this because these two particles they change their flavor. Right, this it was a down flavor quark, it was an up flavor quark. So they change their flavor. So and if we see the mass, there's a mass difference between them. And additionally, it also creates an antiparticle. So this particle which is created antiparticle, it also had some mass, right? So this so it has corresponding energy. So when it's talking about the vacuum, that means just I try to formulate this one that it is when the W minus was created, it was in the presence of the neutron because neutron had some energy itself because it converted for the proton, so it had some energy, and because of that, so it took some time, like 50-minute time scale. So within this 50-minute time scale, it's 50 to 20 minute time scale, it gained the energy because of this reason, it gained some energy, and that energy helped to make this bound state.
Okay, one further question. So
Yep.
this W minus decays into electron neutrino. What is the energy of the electron neutrino? We know the energy of the electron is like zero point 0.5 eV, but then the 80 GeV is there for the W minus. So the neutrino, electron neutrino, anti-electron neutrino should have like a much higher energy.
Yeah, it's of the order of I think 2 GeV. I think it's of the order of one. I think 0.6 GeV. It has an energy scale. If that's the one thing. When I considered when I in the beginning I said this electron neutron, it has a continuous energy.
Okay,
So
so if it is the order of 1 GeV, or like order like the anti-electron neutrino order of 1 GeV, but the W minus energy is 80 GeV.
mhm.
Like why there's a huge difference, and where that energy is again it has gone back to vacuum.
This particle was created. So when they exchange the paper, because this W minus, which is actually a kind of uh, uh, this particle is created with a small time scale, and again it's decay for the time scale. So that energy is needed to do decaying that particle. So there's a threshold. So when the threshold happens, then this W minus is further decay to its daughter particle electron, and this electron neutron, which is enough momentum, enough high energy. That's why whatever the electron neutron is produced at sun with a few microseconds is reached to the earth because it's so high momentum, high energy particle. So if I consider rest mass of neutrino, it's very small because it is of the order of few eV, less than few eV. But the amount of energy it had, so you need to think in terms of energy, not in terms of mass. So it has enough energy, so it can even travel the whole universe within a few fraction of seconds. And it has a so very small cross section that it can travel to everything. So the remaining energy is taken to by this neutrino. Okay. So one more thing I want just to complete this picture. Now, if I try to think the same thing in terms of proton decay. So when I consider electron decay, sorry, not neutron decay, neutron can easily convert to proton because of the mass difference I said. So it had enough mass, like mass difference is of that of 1 MeV. So this additional fraction of energy is provided the enough boost so that this W minus particle can create, because then it can get the remaining energy from the vacuum by creating this particle antiparticle. But in case of proton decay, that is not, it is not very often happen, at least in now in our universe, in our Earth. It can happen at Sun because Sun has a huge energy. So when so Sun. So Sun has like a huge energy source, so that can help that one down quark can convert to up quark. So one up quark can convert to down quark, because if I try to draw the same thing for proton decay, so one proton can convert to neutron, and in this case, it create one positron, because the charge should be conserved, right? Because here is positive charge, so there should be a positive particle. Like in this case, could create a negative particle because it is positive proton, so it need a negative electron. And where it is electron neutral electron, so there should be a electron neutron, because this is a negative. This is L minus, L equals to minus 1. So this should be L equals to plus 1. Okay. But in this case, if I just see in terms of quark structure, the proton is two down, say up, down, up, and this will be up will be remain up, this down will remain down, this up will be changed to down. So if this to happen, so it's not very so this one is preferable because of the mass difference between neutron and proton, so it can get enough energy. But in this case, this is not very preferable because the proton has more less mass compared to neutron. So it can happen if there are some additional energy source is present somehow, and then again, if I try to draw this one, the Feynman diagram, then up quark will be converted to down quark. It will be generate a W minus and W plus, because this case it is it was positive particle, so this is negative one, so this should be positive, and then it could further decay to positron and electron neutrino. So, so this is not a preferable one, because, as I said, so this is massive one. So this need more. This needs some additional source of energy, so that this up quark can convert to down quark, which can generate one double plus charge particle, and that can further decay to positron and electron neutrino. But I think till now it is not experimentally observed and it's in different experiment one. But recently now one experiment is set up. It's called Hyper Kamiokande in Japan, which is under construction. Okay. So its last three word is NDE. N is for neutron or nucleon decay experiment. It's called hyper because before that there was something called super Kamiokande. And now they are making hyper Kamiokande. So it's like bigger one in the large volume. So they had more. And this experiment is basically it's under construction. And and fortunately, I am also part of. I'm going to take part of this experiment also to for some construction part. So this experiment is specially developing, and one of the not only goal, but one of the main goal is to study this proton decay. So they try to make it like more abracadabra magical things, so that they are expecting that they can observe proton decay. So if you watch proton decay, so if you watch just to complete, so when in 2015, this Japanese colleague, his name was Takashi Kajita. He was one of the Nobel laureate in neutrino physics in 2050. So when he gave his lecture on the neutrino, when he received the Nobel Prize, so he mentioned that when he was a PhD student, that time his master's thesis was on proton decay. but unfortunately, he did not observe any photon decay. So his thesis was somehow not successful, but he got Nobel Prize because of the Super Kamiokande experiment, which was he was one of the I think not spokesperson that time of the supercomputer experiment. So he received this Nobel Prize, and he now is more interested on hypercamera so that his long time dream could fulfill. So they can observe some experimental signal of photon decay, which is still now they don't see anything, but probably at some point it's possible. Yeah, so it's not spontaneous. It's not why it's not spontaneous because, as I said, the mass difference. So mass of proton is less than mass of neutron. So to uh, do this transformation, it needs additional energy, which will be source, additional source. But in the nucleus, there is no additional source of because mass and proton difference is not different. But it could happen when if you think how at sun not sun but sun is cu sorry sun sun when because sun is the main source of energy, right? And if you see how the different chain of reaction how they generate the energy, that's one of the main source of energy there is photon decay. The photon is converted to neutron and electron, neutron, and muon, and yes, so then there is a lot of chain of reaction, and this is one of the main chain of reaction which generate the energy. But because it's possible there because it had some source of additional energy which can give the boost. Graviton, because it is still yeah still it is imaginary. So it is good in imagination but not yet happened. Yeah, one more thing, just to complete the picture. There is also we learned today about quantum electrodynamics, which basically interaction between charged particle, where basically fermions they are half the spin statistic is half h cross, and they can interact between them. They can exchange photon by exchanging gluons, not gluons, sorry, by exchanging photons as a gauge boson. And when we're talking about this weak interaction, then a down quark or up quark they can change their flavor. So is called weak interaction, or sometimes it's called flavor dynamics, because in this case flavor are changed. Because down quark is changed to up quark changed to down quark. So if one try to understand the flavor dynamics, then they need to study in more details about how the flavor change by the interaction, and the underlying physics is weak interaction physics, and the symmetry and the underlying symmetry is called U2 symmetry. So in the previous case, we said it was U1 symmetry because the photon was only one gauge boson which was exchanging. Here in this case, two flavor was changing down quark to up quark or up quark to down quark. And tomorrow on next class, we'll discuss about more details about strong interaction. Just to before to start the symmetry, because here I am just telling you that there is U1 U2 symmetry, but I'm just telling. But in the next class, I'm going to show literally how this symmetry come into picture, but mathematically when we try to derive some mathematical formula considering phi-4 theory, which is like a simplest quantum field theory. To do this one, we will start with Dirac equation of motion, which is the extended version of Schrodinger equation of motion. We start with there. We will do some mathematical calculation, and this is important at least to do for one in a lifetime to understand how the different symmetry come into picture to complete the story of symmetry. Yeah.
So in books and everywhere, I'm reading SU2. U2 and SU2 are the same.
Uh, not sorry. It's not U2, it's SU2. Sorry. Yeah, you're right. It's SU2. We'll try to understand how to distinguish between U symmetry and SU3 symmetry. for weak interaction is SU2, and sometimes they combine this SU2 with with U1. They make it like a combined symmetry, SU2 with S1, one for the weak interaction, one for the electromagnetic interaction. If one try to combine them, they call electroweak theory. I think this is one of the theory was given by Abdus Salam, if I'm right. They try to give a theory that they can combine the electromagnetic interaction and weak theory so that they can combine with a electroweak theory. Okay, I think their meeting will be start soon. For in the next class, so today was mostly just a very short introduction about the symmetry, just to understand why we should learn symmetry, because it is important, because when you try to understand, if I mean one can easily understand but from the picture, but if one try to understand mathematically with some more abstract algebra to understand how this different interaction happen with different pictures, then the symmetry is very important one. So in the next class, we'll try to do some more mathematical calculation to understand, at least for QED, how this E1 symmetry will be there when I can see, which is quantum chromodynamics, where basically quarks are interacting with gluons by exchanging of gluons, or gluons itself can interact it. So that dynamic and that happen between the colors exchange. And color is not like really color, but it's just naming of the state of particle, which is called color particle and color state. So we'll try to understand in the next class the first thing, what is quantum chromodynamics in a very brief way, what is the underlying symmetry behind them, and then we will try to do some mathematical calculation to understand the underlying symmetry in QED. If we able to understand at least for one, then and also I conservation, that is space symmetry, and time conservation is energy conservation is time symmetry, or yeah, time symmetry. So we also try to understand this one from the mathematical calculation, and also as you asked, what will be happen when there will be no charge symmetry. Actually, this concept of charge symmetry coming is actually beyond uh, quantum field theory, because the charge is considered as one of the fundamental fundamental kind of like fundamental unit. To understand the charge broken, we need to go into more further detail, but I'll give you some hint to understand what will be happen when charge will not symmetric. Usually, in all kind of interaction, in terms of what I tried to give a very brief picture. Firstly, about the Feynman diagram, how one can draw the Feynman diagram, and then at this two interaction, this weak interaction and and quantum, sorry, weak interaction and electromagnetic interaction. The underlying theory is QED and weak electroweak interaction. So these two things is important, because that's actually how that's basically help to make a foundation of the particle physics. So in the next class,
We don't have a separate game. We are like so the interaction with the bosons, the photon as a boson is a QED. Interaction with the quarks. I mean, what boson? The gluons. Interaction between gluons is the QCD, but the W
one interaction actually the when the gluons, this QCD quarks, they can interact each other by exchanging of gluon, and also gluon can interact each other also. So that's a basic, that's a very defined fundamental difference between QED and QCD.
QC, but there is
And
no
in
step for
QCD,
W plus W minus.
in W plus W minus, they are the gauge bosons. I mean, the W plus
Oh,
W minus and Z0, the neutral one. They are just they are very fundamental one. They just create within a fraction of second. They further decay. So the weak interaction is a something different picture. Weak interaction is not something like QCD or QD. Weak interaction, the story of weak interaction is completely different. Also, tomorrow, next class, we'll try to understand one more thing. Uh, just for the record, for at least for one. we will try to understand what is the uh, strength of different in fundamental interaction. If we start with the QED, if we consider QE as a reference frame or electromagnetic interaction as a reference frame, with respect to QED, what is the intensity or strength of electromagnetic interaction with nuclear force and gravitational force? So first we start with strong interaction. I have still 5 minutes, so I can just complete this one. So if I start with the strong nuclear force, okay. So and if I consider the strength of the strong nuclear force as a unit of one, then if I go to electromagnetic interaction, the corresponding strength is of the order of 1 over 137. This 137 is called it's alpha, yes, fine structure constant. And then if I go to weak nuclear force, which is even shorter, which is of the order of 10 to the power minus 6, which is even weaker because it is happened within the. So if I also see the corresponding length scale for strong interaction, it will happen within in the femtometer scale. I mean within the frame of 10 to the power minus 15 meter. When I consider electromagnetic interaction, it up to infinity because the force is G times what I'm talking about, not G. Q1, Q2, 4 pi epsilon naught R square. So it is 1 over R square force. So it can go up to infinity. So it is infinite force. And the weak nucleus force, it is this of the order of 10 to the power minus 18 on the scale of proton 10 to minus 8, 10 to minus 18 meter. And if I convert also complete the gravitational force, this is even weaker. It's 10 to the power minus 38. That's why in the picture of particle physics, this is not come into picture because this is not enough one for us. And it is also up to infinity. And when we consider the this is strong nuclear force, which is the QCD one. The corresponding physics is QCD. This is QED, and this is weak nuclear theory. And if I also consider the exchanging bosons, for strong interaction is gluon, for electromagnetic is photon, and for weak nuclear is W plus minus, Z naught, and for gravitational, we don't know. It's still question mark. It probably could be graviton, but it is still not discovered yet. Yeah, so this is the very fundamental picture of particle physics. So we are today we basically give a little bit introduction about electromagnetic force and weak nuclear force. So in the next class we will try to have a look about strong nuclear force briefly, and then will the main thing what will again I'm repeating several times, but so that I could remember what I need to talk about next class. We will try to do this quantum field theory calculation using 5-4 theory, the simplest one, and I will also use Feynman path integral approach, which is the easiest one compared to other approach, and then we try to understand how the symmetry come into picture, how the how what how the relation between conservation law and symmetry will be there in the picture. Yeah. So so till then, so and also if you needed, we can make one special class where we will discuss more of homeworks and problems, so that we can do more